Need to think a little bit about waveforms just because the terminology does come up. So we're going to be thinking about frequency, wavelength, and the relationship of frequency we already alluded to, that penetration into human tissue, the lower frequencies penetrate better, but resolution of detail, the higher frequencies give better resolution there. If you think about the lowrider that pulls up next to you at the stoplight, do you hear their high frequencies? No, you hear the low frequencies that shake your car. And so that's kind of an example of this lower frequency penetrating better than the high frequency. Well, okay, how do we propagate an ultrasound wave or any sound wave? Why can you hear me talking? Well, it's because we're setting molecules in vibration, and that information is carried out over space. And so if you don't have a medium of some kind, air, water, whatever, liver, then you're not going to be able to transmit sound energy. So can't travel by itself, has to have some medium for transmission. And again, it won't travel through a vacuum. So the example here, the alarm clock going off in here, you're not going to hear it outside because there are no air molecules to disturb to set up the wave that would let you hear it. Ultrasound waves, generally we think about when we generate with the piezoelectric crystals, we have areas of compression and then areas of rarefaction as the crystal goes back and forth. And we display those as the compressed areas as a peak on a sine wave type curve, and the rarefaction areas as the trough on the curve. So again, that's sort of what we can think about the ultrasound going out in these little packets of energy. The frequency is the number of cycles per second. So we'll show, I think, an example that shows it better here. So if you look at this sort of sine wave here, the distance from the same part of the wave to the next wave, same part, we happen to measure the peak, but it doesn't matter. You could measure the shoulder as long as it's the corresponding area, is called the wavelength. We'll talk about that in a minute. And then cycles, one cycle is just one complete peak and trough. And if this represents 1 second in time, one cycle in 1 second, that's 1 hertz. And remember, we're working with megahertz, millions of cycles per second, but that's the idea. The target that we're hitting, if it sends back a lot of information, the amplitude will go up. So that's an indication of how dense the target is in some ways, and we'll look at some examples of that as well. We won't spend time with that, but the idea is a high frequency, so these are going out, if we have the same time scale for both of these, obviously more waves going out per unit of time up here, shorter wavelength represented by the Greek symbol lambda, and the lower frequency waveform is going to have a much longer lambda. Well, that becomes of practical importance for lots of reasons in terms of especially resolution.